information on the country's mineral wealth. It was set up in 1851 primarily to find coal deposits for the railways. During 1851 to 1947, GSI was the only organization to carry out mineral exploration in the country. Major coalfields, iron ore belts, oil springs in Assam, mineralization in Singhbum belt, etc. were some of the classical discoveries by GSI. However, post-independence, with the changing needs of the country, GSI undertook various measures to map the mineral resources of the country and geoscientifically surveyed for an assessment of the underlying mineral wealth, which led to major mineral discoveries like Khitri copper, Hatti gold, bauxite, iron deposit, etc. to name a few, thereby increasing the share of mineral production, which gave a flip to the industrialization of the country and supported the downstream activities. To further augment the mineral resources of the country and map the inaccessible part, GSI in the 70s employed the emerging field of airborne geophysical survey to map the large swath of the country in a quick span of time. It greatly helped in understanding the subsurface geology and exploring concealed deposits. GSI aligned with the country's economic development and long-term national goals, turned their attention towards exploration of marine mineral resources by carrying out systematic seabed mapping. It initiated the mineral exploration within the Indian Exclusive Economic Zone in the 80s. With the state-of-the-art research vessels, GSI has been able to carry out more than 712 cruises within the Exclusive Economic Zone of India to generate baseline marine geoscientific data. Through this, GSI could cover over 1 lakh square kilometers of Indian territorial waters by systematic seabed mapping. At the advent of the 21st century, with advancements in technology, GSI ramped up the mapping work for exploration of strategic and deep-seated mineral deposits in obvious geological potential or OGP areas. The population growth, changing lifestyle, technological progress, and market dynamics have diversified the use of mineral resources in catering to daily needs. Based on availability, the need of strategic minerals or critical minerals has come up. It takes into consideration both economic importance and supply risks in evaluating criticality. The mineral sector in the country has undergone a paradigm change with the prioritization of the exploration activities, as emphasized in National Mineral Exploration Policy 2016 and MMDR Amendment Act 2015. The notion of strategic minerals or critical minerals has come up in recent time. GSI rapidly reoriented its focus in taking up mineral investigation projects to augment some of the scarce resources of the country, namely lithium, rare earth elements, platinum, vanadium, titanium, graphite, etc. To ensure a sustainable supply of these minerals to meet the increasing demand for new-age technologies like wind turbines, electric vehicles, photovoltaic cells, fluorescent lighting, grid storage batteries, magnetic refrigeration, nuclear power, GSI, for the sustainable development of the entire ecosystem associated with mineral and mining sector of the country, is providing reliable geological data and information along with digitized maps and plans to different stakeholders free of cost. From a humble beginning to adapting towards modern-day needs of the country, GSI has remained ever so committed in nation building and economic prosperity.
Hello? Okay, thank you. Uh, so I am Pantick Santra. I am a geologist in State Unit Karnataka and Goa. Okay, so today my topic is structure and deformational history of the Western Dharwar craton. Now, whenever we read or study about the structure, we see so many equations or notation in the book or maybe in the lectures. But this lecture, I am prepared very basic things. So I will not bore you with all those equations, right? So I mostly deal with the field-based things and will show you some photographs. Okay. So whatever doubt you have, you can ask anytime during the lecture or after the lecture. So you guys are very much familiar with these two maps, right? So now focus on the left-hand side. So here we can see that peninsular India is there. Now what is peninsular India? It is made up of the oldest rock present in our uh, country, or maybe the part of the original Indian plate that was present for the collision with the Terrane plate. So now after the collision, there was the rise of Himalaya, and we call it extra peninsular India, right? So now the extra peninsular India is high in the high altitude. So the rivers are coming from there, dumping all the sediment of the peninsula, and it's covered a part. And it's so huge, so we call it a different name, that is the Indo-Gangetic Plain. So this part covered a part of the rocks of the peninsular India. So what we have today, the south of this Indo-Gangetic Plain, and the rocks of the very old age are present here. Now, what kind of thing made this peninsular India? This is we call Proto-India. Sometimes you will get in the various literature. So now the Proto-India is made up of some cratons, obviously with the mobile belt. So some silt, as Rovi said, terrain also, that is the eastern Ghat mobile belt and the southern groundite terrain. So there are major six, or some people call it six and some people call it five. So we are not getting in that debate. So Dharwar, Bastar, Singhbhum, Aravalli, Bundelkhand, and the Chotanagpur craton. These are the major oldest cratonic block of India. Okay, so and all those are bounded by mobile belts. And now, as we call like Dharwar, so Dharwar is also not alone a single block that is evolved in a single day. So it is also made up of very much smaller block which got accreted with each other with time. And today what we see, we will discuss. So whatever the rock is present in those cratons are very old, right? So they formed during the um, Archean. So we'll get a very much history from, if we study all those rocks seriously, in a manner, in a geological sense, then we'll get all the history of crustal growth, deformation, and then destruction from the beginning of the earth. So this is the whole Dharwar craton. The map is here, and it encompasses the 45 million square, 0.45 million square kilometer area, and it nice. We will get greenstone belt, some kind of greenstone belt, and it is then later included by very kind of calcaline granite and highly potassic granites. And all those things, how it formed, how it deposited, and what is the intra-relationship already discussed by my colleague Ravi. So I hope you guys enjoyed that lecture, and now I will tell the structural part of this craton. So as he said also that the southern part of our Dharwar craton is bounded by the Pan-African mobile belt, and the northern part is covered by the Deccan Tract. So we don't know actually the Dharwar craton ends at the north, as it is covered by the there will be some Proterozoic sedimentary basins and the Deccan Tract. The eastern side, it is very much clear. It is bounded by the Eastern Ghat mobile belt, whereas the western side you will get the Arabian Sea, But again, the problem comes to the southwestern and the northwestern part. And right now I am associated with a project, STM project, where we are trying to find out where it ends at the southwestern and the northwestern part of the Dharwar craton. Now, again, within the Dharwar craton, as we are saying, so it is the greater Dharwar craton. So within the Dharwar craton, there we are dividing it again in the eastern and the western Dharwar craton. So, and from where it is, where the boundary is, it is comes from, okay. So it is coming from this line, and we call it the Chitradurga eastern margin shear zone. Okay. Now we know that it's a Archean craton, no problem in that, and it preserves the Earth's oldest history. But what to study there? Because you know this, but how to know that it preserves oldest Earth history and how to recover this history? So we have to study the lithological association along with the structure. So if you just do the lithology, you will don't get, okay, like you will say there is some granite is there or maybe metabasalt is there, but how it's structured, if you don't consider that part, then the study will be not completed. And then again, you have to study the metamorphic part, because all the rocks we are seeing in the Archean craton all are metamorphosed. Okay, so we have to study everything in together, that is lithology along with the structure and metamorphism. Then what kind of knowledge we will gain? Right, we will read this lithology, structure and metamorphism, that what we will get to know. That is the how the craton evolved with the time. So with the time, there was any change in tectonism or not? With time, there was any change in the pressure direction or not? And whatever change in the system, what was the change in the geodynamic position or whatever the change in the geochemical situation, so, and what kind of lithology formed at that time. So now, who is responsible for the development of structure? There is only one thing who is doing all those things, that is called deformation. So deformation, you can say any kind of deformation, like from our daily life to geological scale, deformation means whatever the form was present, we are changing the form, right? So now what kind of deformation? So there can, in general sense, we can say that is homogeneous deformation or heterogeneous deformation. So from this picture, this is very clear. This is we call homogeneous deformation, because what? Before the deformation, we have all these circles, and after that, it became ellipse. Now check, all the ellipse looks equal. So this is called homogeneous deformation. So like if in this lecture, if all the people are equally attentive and getting the benefit equally, then we can call it homogeneous, homogeneously benefited session. Okay. And if not, like someone is getting benefited more and someone is not interested, then we can call it heterogeneous. Like in this figure, so some are became the ellipse, like this kind of thing. Some become small, some become big. So each part of this body, the strain was different, means deformation was different. So we call it heterogeneous deformation. Now again, see that the lower part. So first you have this circle in both cases, and then you are ending up with the ellipse. But what is the difference is that in one case, it's became the perpendicular, it remains perpendicular, right? So from the first photo to the last photo, all the axes are perpendicular from where we started. But in the lower case, we had a circle, we are getting an ellipse just like the first time, but the axis is not perpendicular. So if the axis remain perpendicular from the in comparison to the first picture, so we call it coaxial deformation. So the perpendicular line remains perpendicular, whereas in the later, the lower part, we had this perpendicular axis, right? The bounding square of the circle. But see at the last photograph, what we get, we are getting an ellipse, but the bounding box is become, it's not a square. So the axis is changed. In that case, we call it non-coaxial deformation. So where the perpendicular line not remain perpendicular, we call it non-coaxial. Now what happens? There I will introduce to a new term that is called progressive deformation. So whenever you are starting a deformation, so till a point, everything will be homogeneous, maybe. So there will be some changes also, but see from this point, one is giving the coaxial deformation, and in another case, you are giving non-coaxial deformation. But all the things are homogeneous because see, all the circles become ellipse and all are identical. Okay, but with time, when we increase the, we give the deformation with infinity time, then within that mass will get some heterogeneous deformation. Like, see, these are circle, but in this case, this is became the ellipsoid. And here is the same. So with time, anything can be changed. And this time means the geological time. Now, what is progressive deformation? Progressive deformation means you are putting a rock under pressure for a very long time and you are not releasing from the pressure. So this case generally happens in the high grade terrain. Like Ravi said that the southern part of the Karnataka or the Dharwar craton is made up of granulite. Now what the granulite forms at the lower crustal part. So the pressure temperature condition is very high in that point or in that region. So and in every instances the flow can be changed. The mm, flow means you are giving the pressure to the rock and the rock is behaving in a certain way or changing its form in a certain way. Okay, but that flow direction can be changed anytime. And what is the another thing we call that episodic deformation? Like there, the rock is putting in a certain time is given to a rock, and the pressure direction will be same. And then there will be seizure of the deformation. Then again another phase of deformation will start. So like you have a this sphere. So now you can make this sphere to this ellipsoid by one day. Okay, and in that day you are giving a continuous pressure, not very big pressure, but you are giving a continuous pressure. Or maybe you can change it like around 10 a.m. you are giving some pressure, around 12 at noon you are giving some pressure. So you can make the ellipse, you get the same result, but if you are doing something different. In one time you are giving a continuous pressure, and in another case you are giving some episodic pressure. So now what happens when the rock is subjected to so much pressure or whatever is happening to a rock, it can store a finite things within this. So what it we call like, if you have a pen drive, probably it can store a 64 GB memory, or probably you have some 5 GB memory or 128 GB memory, whatever. So there will be a finite memory of a rock, or maybe you can call we can recover a finite thing from a rock by starting this. So, and what happened? Whenever the next deformation comes, the memories of the earlier part can be erased. Erased by what? So there will be some structure of the earlier time. With the next phase of deformation, it will change all those structure or modify all those structure. Okay. Or maybe it formed by the progressive deformation, like it started from the northwest, southeast kind of pressure, directive pressure, then it can change change any time within that progressive deformation, and the earlier memory can be erased. So what we do? So if you are working in an area where you know that there will be some complex history, and in the cratonic part of India, obviously there is so much deformation history, so you have to always give the special attention where the strain was low, means that deformation part the intensity of the deformation was little low to get all the memory, all the history, right? So where you will get that D1 or D2, D3, whatever you want to call it. So that D1 will be there, D2 will be there, D3 will be there, where all things are present means uh, all no one erased the earlier deformation. Okay, so that we call the low strain zone. So we have to check all this low strain zone to get all kind of history. And if you want to get the history of only D2 or only D3, then you have to check all those areas where that is very much prominent over the other one. Now, what is the, so we know now there will be some kind of deformation, and deformation is only creating the structure. So how we'll know what are the manifestation of deformation? So it will form some planar structure or linear structure, or at the end it may form some shear zone. That could be that we call foliation, right? Now foliation can be various type. It could be slaty, philitic, schistosity, or gneiss. So when we call a rock, maybe like you are in a field and you are describing a rock. So when you will write it's the rock contains slaty cleavage, or the schistosity is present there, or the gneiss is present there. It depends on what kind of rock you are seeing. So slaty or philitic, slate, you already know this, all these terms are related to the metamorphic rock. So at the lower grade, when you are getting some slate, so whatever is present that cleavage we call slaty cleavage. And when there is some uh, mica development started, then it creates a philitic scene, right? So in that case, what kind of fabric we got within the rock, that is we call philitic cleavage. So from here to here, from slaty to gneiss, the grain size is increasing actually. So in the schistosity, we are getting the rock is dominated with the mica. So it is, we call this schistosity. And whereas in the gneiss, all the minerals became equal, equidimensional, but there is some difference in color. It may be in color or it may be in composition, whatever is present there. So we call it gneiss. Now, how it formed? So like you people are present in a room and someone is pushing you. So first, and you will try to arrange yourself in a fashion so you can uh, arrest that pressure. So for that, what you will do, you will parallel your chest or your back to the wall, right? So the mineral do the same. Whenever the pressure is coming, and if there is some parallel, plated kind of mineral is there, they will try to uh, parallel itself. So it will arrange themselves in a fashion so the force became perpendicular to their face, or and again how it formed, that is a segregation. So there is a pressure, and maybe uh, the mafic minerals will say, okay, we'll go together, and the felsic minerals will say, we'll go together. So there will be some color banding. It can form by melting also, like there will be at the lower crustal level, the rocks start to melt, and the newly formed leucosome will create a band, like it will inject it within the rock again. So there will be a color banding again, but it is by melting. So the leucosome will be the lighter tone, and the melanosome, what is the earlier part of the rock, will be dark color. So now see, this is a photograph. It's a photograph of a granite. So we can call it, some people will call it, it is undeformed, or maybe some people will call it is undeformed, but these feldspar clasts are arranged in a certain way, not very prominent, but there is a crude alignment you can see from here, this direction, right? In the next case, you see This you can see a color banding. So this is a gray color, dark gray, and this is relatively lighter. So this is a color banding, and so there are two kind of color banding actually. Whatever you are getting these bands, these are the later leucosomes or maybe a leukocratic band. And within this part, you can closely look and say within this gray also you are getting some kind of banding. So actually this is a nice from the markera area, and within that some kind of leucosome or maybe granitic composition included later part. So there is a two kind of banding we are getting. Next again, it is again from the markera area. So this light colored band, we call it leucosome. So these things formed by the melting of the rock, and that is again included within the rock. Right. So this part we call the melanosome, and this part we call leucosome. And again, see here you can see that all the fabric, whatever present in the rock, is very much continuous, very much thin, and very regular. Okay, so it is very thin, very regular, like the pages of your book. So this kind of foliation, whenever you find in a rock in your field area, so you have to be very cautious, because this kind of regular thing, which is very much continuous and which is very much prominent, only can be found by the shearing. In most of the cases, I can't say only, but in the most of the cases, shearing only enhanced this kind of fabric. So actually this rock and this rock, they are same, but this is formed by the melting. Okay, and here that same fabric got modified by the shearing. Okay. So now see, in this is all the thin section photograph. Okay. So in that case, you can see only few biotites are showing a crude alignment, right? And this, that gray color and the light color and these dark color minerals are quartz feldspar. So they are not showing any kind of deformation signature, or they are not showing any kind of um, uh, alignment, whereas the biotite is only showing some alignment. Now focus on this picture. You can see the quartz and feldspar, they are also showing a alignment, right? It is very clear, right? So this thing, and we saw those two photographs in last thing, this. So the first thin section photograph is from this area, and the right photograph is from the sheared area. So this kind of texture, whatever you are finding, getting in a rock in the outcrop level, you are getting the same in the microscope level also. So there is a main key term. Whenever you are calling a fabric of a rock, then it must be pervasive. Pervasive means it should be present in any scale, starting from the outcrop scale to the microscopic scale. Then again, this is also from that first query photograph. So here you can see that garnet, this is garnet, this pink color mineral is garnet, and this is mostly biotite. And the lighter color is made up of quartz and feldspar. So you can see that biotite is giving a planar orientation. Okay, and the garnet, all these garnets are not deformed, but they are forming along a zone, right? So they are giving a fabric within the rock. Now this is from the sheared part. So see here the garnet is also present, and these things, whatever you are seeing, some ellipsoid or the rounded thing, these are some quartz and feldspar. And the other part of the rock, like here you can see that quartz feldspar is so much big, but here all the things became so small because the shearing was there, and it reduced the grain size. So we are getting some relic of garnet and quartz feldspar, and the other part is the grain size reduction was took place, and it is now defined by some kind of micaceous material. Then if you got a foliation in the field, how to record? Means how probably you saw foliation in the field, but ultimately you have to record on your notebook, right? So what you should write? It's made up of what? Okay. So you are getting some planar structure. It is defined by what? So is it defined by if some intrusion of some white veins or white leukoplatic bands or leucosomes or not, or it is made up of color banding? If color banding, then that within the dark color, what kind of mineral is present, and in the white part, what kind of mineral is present? You need to note it down. Then it's continuous or not. Like you can trace it for a continuous or for a considerable length or not. It's repetitive or not. It's thickness. So the thickness means if you are getting it's in a regular structure data, what we actually record from the Branton compass, and in GSI we have a practice, we don't write down the data, we draw the data. So because like where is the pen? Okay, like if you get some east to, so first, sorry, it's not east to west. Okay, this part, consider this one. So we do this, and if it's dipping towards south, we do these things. So we don't write it down. We do the strike here, and if it's not perfect, we just write it down 270 this part for the strike and the amount of dip here. From today, you start also this practice. Don't write it down, just draw it. And then comes the fold. And these two pictures are not from the Dharwar. I took it from my. You can see that how big these folds are. Okay, so this is one we called antiform, right? And here you can see a synform. So this much big folds can be formed in the nature. Now, so what is the if like you may be asked in the UPSC interview also sometimes, what is the definition of a fold? So there should be some keywords. Okay. And you can find it in any kind of textbook that there will be. So you just can't say a surface which is not planar is folded. In the geology, we don't consider them as a folded surface. Because in the fold chapter, you can see it is very clearly mentioned the initial curvature of a stack of layer is changed by the deformation or enhanced by the deformation. So if the initial curvature was there by any means without deformation, we don't consider it as a geological fold. So the deformation should be increased or maybe the curvature should be enhanced by deformation. Then only we consider it as a fold, right? So here I have some photographs. These photographs is from Chittorgarh Shear zone, and we can see how the BIF is folded. Now all the layers within BIF is made up of what? One layer is made up of iron and another layer is made up of silica, right? So you can see various kind of fold is present here. Next, this fold is from Markara shear zone again, and you can see this folds is defined by some white color band and dark color band. So here also it was same, some white color band and dark color band. It was what? It was the bedding plane, right? Because it was the original structure of the rock. It was present from the deposition of the rock. So there will be some dark color and white color band, and here we are getting also some dark and white color band, but this is made up of CRE. And these rock types are different, right? This is a nice, and that was from BIF. So this kind of fold you will get in the high grade terrain where the nicosity of a plane that we just discussed in the last few minutes ago, that a fabric of the rock is deformed, right? And can anyone tell me that what kind of fold this one? If you can unmute and tell me. Hello. Okay. So we can see from this picture. Just a minute. Sorry. Okay. So actually, this is what we call the fold axis, right? So this is perpendicularly going down. So we call what this kind of fold? Okay, we want the answer at the last, right? I'm not going to tell you what kind of fold it is. The axis is going perpendicular towards the down. So you have to tell me at the end. And this is again the fold is there. And see this thin black color things, actually those were dyed at some moment. And how I am telling this, because whenever we got this kind of things in the field, there are so many chances what it can be. It could be the part of the gneiss, or it could be something into that they got folded. So these actually were some diglets, and they are folded within the rock. And here in the right, again you see, so folds are there and formed by the, defined by the gneissosity. Again you can see some folds, and they are showing S fold, right? And these are made up by a ultramyelinite. Now, how to record the data of a fold at field? So suppose you saw a fold. So first you have to write it down that it is defined by what? Like who is showing the fold? The gneissic banding, or the layering within the BIF, or it could be some quartz vein within a rock is folded and the rock is not folded. So you have to write it down everything. Then comes the geometry. So the hinge of the fold is thick, or the hinge is the thin, the limbs part are the thick. All those things you have to write it down. And then there are some classification of the fold that is called the Ramsey classification. So you have to name the fold depending on that. Then comes that antiform or synform, then the vertical fold or not. All those things you have to write it down. Then comes the structural data. So you have to take the data. In a fold, there should be some planar data and some linear structure, because you are folding a plane, right? So a planar structure is getting folded. So some linear structure will be generated along the axis of the fold. So that is we call fold axis. So you have to take the structural data of the fold axis along with the axial plane. Now, what is shear zone? If anyone asks you what is shear zone, there should be two keywords when you are answering that question. That is, it's a high strength zone and it's a curvy planar zone, right? So, and from this picture, we can see when we are going down, that is, we are going to the lower crustal rock from the upper surface, the shear zone became much wider and it's become anastomizing, right? So if you are working in a high grade terrain, in a granulite terrain, you should know that the shear zone should be much wider than if you are working in the Chitturga area, where we are getting some greenstone kind of metamorphic condition. So when you are going to the deeper crustal section, the shear zone will be much wider and much anastomizing, right? So the shear zone can be three types in general. It could be ductile, and it could be brittle ductile, and it could be brittle. So ductile means when the continuous flow of material. Now when it will happen? When the pressure temperature is high. And the brittle is when the pressure temperature condition is low. So from the last slide, okay, so when you are getting the shear zone in this part, you may got the brittle kind of thing. In the between, you will get some brittle ductile shear zone, then you will get the ductile shear zone till the end. Okay, and these are some field photographs. These are from ductile shear zone. And here you can see, okay, from this photograph, it is very clean that this fabric is coming, then it is bended, then you are continuously getting this here. So there is some bend, right? And here you can see, okay, there is a bend of this thing, this pink color of vein, this is bend, and here a bend within this white color band. but there is a displacement also. So we called it brittle ductile shear zone. And at the end, you see that only you can get some displacement, no this kind of bending or all those things. And so we call that brittle shear zone, and these are actually fault zones. So from here to here, what is the difference? Here is only displacement, but here it is continuous but with some changes in its orientation. Now, I am not going to deep all these things, but you know, within the ductile shear zone, if like if you are working in an area where your ductile shear zone is present, so you have for all these SC planes, then the lineation, all these porphyroclast or blast, mica piece, sigmoidal veins, all those things. Okay, and I also few photographs. This is again from my field area. This is a thin section photograph of the ultramyelinite and the same rock in the field. So you can see that ultramyelinite is again folded, okay, very tightly folded, and you cannot. And here you are. Sir Uttam Patel, can you mute yourself because some sounds are coming. Thank you. So in the ultramyelinite, you will be very lucky if you get some grains like this, and the rest of the things are very fine, and you cannot identify any grain under microscope also. So this kind of thing only can be done by shearing only. Okay. Now here is the again in this rock you can see the quartz. These things are quartz, and we call it quartz ribbon because these are stretched and elongated, okay, along a particular direction. And you can see the same within the thin section. See, these quartz are this much elongated or stretched. Again, these are some porphyroclast, or sometimes we call it some rigid body orientation, and they are showing some orientation. Orientation means the kinematics of the shear, like how it was. It was dextral or sinistral. Okay, so from this picture we can see it's clearly sinistral. And here we are getting some SC fabric. So this was the original fabric of the rock. Then the shearing was like this. So we are developing another plane like this. Now I'm just skipping this picture because I think I'm going very long. Now just concentrate the general structural pattern in the Dharwar craton. Now why I am calling it generalized? Because Dharwar craton is made up of so many small parts. And now the structure of the Dharwar craton changes in various places. But we have to do some generalized things. So for the basically for the student, when we are writing it or whenever doing some exam, so we should know the general pattern of any area actually. So as Ravi said, there are two kind of beamstone belt present in the Dharwar craton. So one is the Sargur kind of thing, Sargur times, that was the older one, and then the Dharwar, that is consist of Chitradurga and Bababudan. So in the Sargur, what we are getting from the D1 in Sargur, the earliest it is within the Sargur, and a penetrative cystosity is formed. Now from the term you can think that what kind of rock is present there. Whenever we are calling cystosity, means there should be some rock which contains some micaceous mineral, so that's why we are calling it cystosity. Okay, and the cystosity is parallel to the bedding or the lithological boundaries. Then we are having some axial planar type to isoclinal small scale fold. No regional fold is identified from the D1. So the interpretation can be anything, that no regional form was formed during the D1, or maybe they are modified during the next phase of deformation. And what was the metamorphic condition in D1? That is the amphibolite phases of metamorphic condition, upper amphibolite. So we are getting some migmatization, means the rock started to melt. Then comes the D2, where we are getting the upright tight isoclinal fold and the north-south striking axial planes. So the D2 is determining structure of the whole Sargur belt. So you can see the Sargur, the meta sediments and the meta basic ultramafics, they are mostly present along parallel to D2. So they are uh, actually responsible for the structure of the Sargur. Now again, what written here, a mineral lineation is coaxial with the SGD2, the D2 deformation folds, but no penetrative cystosity developed. So in the D2, you will not get a proper plane, but some lines are formed. So we are saying what constriction type of strain is there. So linear structure formed, not the planar structure. That's why we are calling that constriction type of strain was there, whereas in the earlier case there was flattening strain because we were getting some planar structure. And here also the metamorphism condition was amphibolite, but the anastasis or the migmatization was very less. And in the D3, that is the obviously there the earlier structure, whatever present, and that time retrogression took place. Now, what happened in the Dharwar rocks? That is the Dharwar supergroup that consists of Chittadurga and Baba. And the long study within this Chittorgarh area shows what the no structural discordance between the Baba Budan and Chittorgarh group. So the Baba Budan group deposited earlier, then the Chittorgarh group, but there was no structural discordance. Means whatever fold is present in Baba Budan, you will find that in the Chittorgarh also. So both of them are deformed together. Then three phases of deformation is mainly identified, that is D1, D2, D3, and the D2 deformation controls the regional structure. So whatever you are seeing this kind of a structure, that is north-northwest or south-southeast, that is mainly controlled by the D2. Then what kind of deformation one present in this Chittorgarh area? That is a planar slaty or cystosity. Okay, so what kind of in what kind of rock you will get the slaty cleavage where the grain size is very small, whereas the cystosity means the mica is there, grain size is relatively much bigger and mostly transposed S2. So what we are saying that S1 was there and they were transposed by the next stage of deformation. And the small scale, small to outcrop scale, plain cylindrical to strongly non-cylindrical folds. So in that case, in the D1, we are getting cylindrical folds also and non-cylindrical folds also. And then these are present as rootless small folds, and there will be some 1B and 1C geometry depending on what kind of rock we are seeing. So like in a competent rock, there will be different geometry, and obviously in an incompetent rock there will be different geometry because the competent rock doesn't flow. Okay, it's just folded. Whereas the incompetent rock, the hinge will be always much thicker in comparison to a competent rock because the material flows towards the hinge. Then the D2, and so in case of D2 in Chittorgarh belt or the Chittorgarh belt or the Bahubudan belt, the D2 is the major deformation and who is responsible for this kind of structure of the Chittorgarh belt. So this is a regional kind of thing, and you will get some strong axial planar granulation. So wherever you walk the field in Chittorgarh area, you always get a very much prominent structure that strikes northwest to southeast. Okay, and the folds within the Chittorgarh area, they are large scale. So you can see one fold closer is here, one fold closer is also here. So these things can be seen from the satellite imagery also. You can see in the Google map all these folds. Okay, so now within this fold you will get obviously some smaller fold also in different scale. So these folds are non-cylindrical in regional scale also. And the superposition, obviously, you probably heard the superposition of fold. That means the one fold was present, then another deformation took place. So there will be some fold interference pattern. So that is also present in the Chittorgarh. So now comes the D3. D3 means the last part of the deformation, and where the D3 is majorly associated with some shearing in the Chittorgarh area, right? Now, how this granite greenstone terrain in the Dharwar craton evolved. So there are some models. One few group of people say that subduction model means there was some tonalitic or granitic basement. Okay, over which the deposition of this greenstone material started to take place. So there will be some intermediate mafic volcanism, and there will be some sedimentation. Okay, and with time, due to the gravity, that basin will be going down within the softened basement. Okay, and then at the last there will be some deformation. So this thing is called subduction model, and those group of workers didn't believe in the plate tectonics model in that time. That means that time is the Archean time. Whereas the another group of people says no, there was no subduction model, and they are saying there was some so much folds are there, and so there should be some plate tectonics in the Archean, and there was some crustal shortening and thickening. The crust. Okay, so the plate tectonics model, so the crust is shortening means it gets thickened because of the convergence. Okay, so now this is the Terrane accretion model, like how the how the EDC and WTC, what we are saying today together, how it came closer. So some people believe, okay, the EDC overrides the WTC through that along the Chittorgarh eastern margin shear zone. So we are seeing some folds. Okay, so these are overriding over this western part, and along this shear zone there was some shearing granite intrusion, and within this granite we will get all kind of this sinistral geometry. So we are saying there was some sinistral movement. Along with that, the EDC was overriding this WTC. Whereas there is another group of people, they also said, okay, there was plate tectonics theory, but the EDC actually going down to the WTC, and the WTC was the foreland basin for the EDC. Okay. So now if we integrate all those studies, what we are seeing, the recent data, just so what we are getting, that the Archean crust is exposed in the Dharwar craton, no doubt in that, and it's an oblique section showing the middle and the lower crust of the Earth, and it's showing a billion years of history, starting from the Paleo-Archean to the Neo-Archean. Then two major episodes of juvenile crust accretion. Crust accretion means what? The crust means that felsic crust is forming. Now, when the 3.45 to 3.15, when the PGC1 form, and then the 2.6 to 2.5 when the PGC2 and the closed bed granite form, and there was some minor event in between. Okay, and the major crustal reworking was in 3.1 and 2.7, means there was so many things are going on in this time. Then a vertical tectonic regime was there. They said when the Sargur formed, and the deformation history of the Sargur is mainly controlled by the subduction process. Whereas around 2.75 the plate tectonic started. So the Dharwar group of super group of rocks, whatever you are getting that structural things in the Dharwar supergroup is formed due to the plate tectonics in that region. Now, what is the present configuration? Represented oblique cross section of the continental crust. Now, why oblique? Because in this crust at the Dharwar craton in the northern side, we are getting some green schist phases of metamorphism, whereas at the southern part we are getting granulite craton metamorphism, and there was no break within this craton. So what we are seeing, the lower continental crust is exposed towards the southern part, and the upper continental, sorry, not upper, the middle to upper part is exposed at the northern part. So there was some tilting. That's why we are getting all those things today on the surface. now the metamorphic event culminated development of east-west trending Chernobyl belt. So there was some at the southern part of the Dharwarian, we are getting the Chernobyl belt, means the granulite kind of retaining the north-south trending craton fabric. So within that Chernobyl also we are getting this north-south kind of trending fabric. So there was no discontinuity, right? So that's why we are calling it, there was a tilting. And obviously there was some difference in the metamorphic phases from WTC to EDC. In the WTC, we are getting intermediate pressure temperature, that is kyanite to sillimanite, whereas you can see in that kyanite sillimanite and andalusite phase diagram, that kyanite to sillimanite, you can transform it from kyanite to sillimanite at intermediate P and T. Whereas from the andalusite to sillimanite, you can do at low temperature but low pressure but high temperature, right? There is some interesting thing I just want to share with you, because this Bessier, in his book, he wrote it down. Interpretations are state of the art and not necessarily be the absolute answer. So whatever we are studying today about the structure or about the anything in the Dharwar craton, the observation remains same. Okay, so all the people are going to the field, they are seeing the same rock. They are noting down the same structure from the field, but the answer can be different. So maybe in the field you are seeing two parallel lines or the planes at the field. Now what can be the interpretation? That both the plane or lines form together. Okay, there could be one interpretation. The interpretation two can be the later deformation transposed all the earlier fabric. Okay, and make everything parallel. And there could be some interpretation three also. The later planar followed the preferential orientation formed by the earlier one. So see, like interpretation 1, 2, and 3, they are some three people. They went to the field and they saw only two parallel things, and that interpretation can be changed. Okay. So whatever you are seeing in a field, you have to observe and note it down properly. So that's the end. Thank you. And any question? So please, you can ask me, or you can ask to ask me as well. Thank you.
Thank you, Pantick sir. So, on behalf of GSI, on this occasion of Bharat Ka Amrit Mahotsav, I would like to thank the speakers, Sri Ravi Tripathi ji and Sri Pantick Santra ji, for their time and effort to share their knowledge, thoughts, and experiences on geology and stratigraphy of Western Dharwar Craton and structure and deformational history of Western Dharwar Craton. I would like to extend my vote of thanks to the participants from various universities who have graced this online lecture event. We strongly believe all the participants would benefit from the knowledge shared by the distinguished speakers. We wish to see you tomorrow with same enthusiasm, where we shall be discussing about granite and granitoids of Western Dharwar Craton and the mineral potential of Karnataka. Thank you. Jai Hind.